Hello, everyone. Salutations. Waiting for a couple more viewers. Oh my gosh, Hazel's farting. It's like filling the whole room. How is a small dog filling the entire room with that smell? Holy cow. Hello. All right. So let's go ahead and get started. And we are going to, this is our third lecture on energy. And we are going to start off with a little bit of mathematical background. And this is going to be review for the people who have already taken calculus. But if you are concurrently taking calculus, then I don't think you've gotten to this yet, and we're reaching a point in the course where I can't avoid it any longer, and we have to talk about what's called integration, okay? So integration is the reverse of differentiation. This isn't that bad. Don't worry about it. You got it. So it's the reverse of differentiation. So and it has a different symbol. Okay. So the way that you write an integration is integral of a function d variable, where the variable is the variable that you're integrating over. So if it's a function of x, then it would be dx. If it's a function of time, then it would be dt. So whatever you're integrating over, it's going to be that, okay? So we are going to have really simple functions to begin with. And this is the only type of function that you have to worry about today, which is a power law or a polynomial function. So let's say you have a function ax to the n. So we're going to integrate ax to the n dx. Okay? So the rule is, remember, when we differentiate, we bump down the power. In integration, we bump up the power. Okay? So x to the n plus 1. And then remember how in differentiation we multiply by the power, but in integration we divide by the power. So it's going to be divided by n plus 1. Notice that we divide by the bumped up power. Okay? So, for example, what if I had the integral of, let's say, 3x to the 4th dx? Okay? Then that's going to be equal to 3 times x. I bump up the power, so x to the 5th, and then I divide by the bumped up power. That's the answer. Okay? If you have a sum, so this is for a single monomial, a single term in a polynomial. It's called a monomial. So a single monomial. What if you have two terms? So for example, what if it was x minus 2x cubed dx? What is that, the integral of that? Well, I'm going to bump up the power. This is x to the 1 power, remember? So I bump it up and I get x to the 2 power. And then I divide by the bumped up power. Okay. And then I just do the same thing for the second term. So I have minus 2x, bump up the power, 3 goes to 4, and then I divide by the bumped up power. Okay? So that's how you do, that's how you integrate polynomials. There is a special kind of integral that is called a definite integral. And so a definite integral is written with numbers above and below the integration sign. So maybe I have the integral of 5x to the 9th dx, and maybe I integrate it from 1 to 2. Okay, so this is called a definite integral whenever you have these numbers. Okay, this is called a definite integral. And so what we do is we do the integration just the same way as normal. So we bump the power up by 1, so I have 5x to the 10th divided by, and then we divide by the bumped up power. And then we evaluate it from 2 to 1. Okay, so what that means is you are going to take this function that was the result of the integration, and you're going to plug in 2 to that function, and you're going to plug in 1 to that function, and you're going to subtract them. Okay, so it'd be 5 times 2 to the 10th over 10. So I plugged in 2 minus 5 times 1 to the 10th over 10. So I plugged in 2, I plugged in 1 to my function that was the result of my integral, and then I subtract those two. So it's top number minus bottom number. All right? So that's how you do a definite integral. Boom. So we need to do integration for the lesson today. Greetings from Africa. I don't know what that means. Okay, so today's lesson is going to be about what's called work. Okay, and so work is closely related to potential energy. The definition of work is it is the integral of force as a function of position dx from A to B. So the work is a definite integral of the force as a function of position. That's what work is. So this is our main equation for today, or one of our main equations for today. All right. So the units of work are the same as the units of energy. So the units of work are joules. And let's just do an example, just a really simple example. What if you have, so there's a good question. So is work equal to negative potential energy? No. So you could basically think about the potential energy as an indefinite integral of the force and work as a definite integral of the force. Okay. So let's suppose that the force as a function of position is given by 3x. Okay, and by the way, I should say A is going to be the initial position of the particle, and B is going to be the final position. Okay, so calculate the work. Done by this force. Okay, as the particle goes from x equals 1 meter to x equals, let's say, 3 meters. Okay, so when we're solving this problem, we would say work equals the integral of the force field, which is 3x dx, from 1 to 3. Okay, so first step is to just find the integral as you would usually. So we x is just x to the 1 power, so we bump up the power by 1, 3x squared, and then we divide by the bumped up power, which is 2. And then we want to evaluate it from 3 to 1. So that means we plug in 3 into this function, so we have 3 times 3 squared over 2. And then we subtract the same function but with the bottom number plugged in. So minus 3 times 1 squared over 2. So this is going to be 27 over 2 minus 3 over 2. Okay. And so 27 minus 3 is 24, divided by 2 is 12. So 12 joules. All right. Hang on one moment. I got a text message that I need to respond to. Okay. Sorry about that. So that is how you do work. Now I want to talk about something called the work. Well, first of all, let me talk about the net work. So the net work, so this force right here might be one of the forces acting on the object. Okay, there could be more than one force. So individual forces do work. Okay, individual forces do work. So if this force happened to be the net force, okay, then it would be the net work. So the net work is the work done by the net force. Okay? Is it 9? I don't know. If I made a math mistake, then I made a math mistake. Who cares? It equals a number, all right? The work done by the net force is called the net work. Okay, so I will call that W sub net. And there's a nice little theorem. It is called the work kinetic energy theorem. And I'm not going to prove it. It's basically the same thing as the proof of conservation of energy. So you could actually probably prove this yourself. It's like the proof of conservation of energy, but in reverse. So I'm not going to spend time proving it. But what it says is that the work done by the net force is equal to the change in kinetic energy of the object. Okay? So work is equal to the net work is equal to the change in kinetic energy. So let's do an example. All right? So that example is, so let's suppose that we have the net force as a function of position is 3x. Okay? So we're using the same force as in this example, but now we're saying that this is actually the net force. Okay? And so let's suppose a 2 kilogram particle with initial speed, let's say, why not 2 meters per second, moves from x equals 1 meter to x equals 3 meters under the influence of this force. What is its speed? When it arrives at x equals 3 meters. Okay? So because this is the net force and it's going from the same starting spot to the same ending spot, I can just immediately say that the net work is equal to 12 joules because that was the answer from the that was the answer from this example. Okay, so I know that the network is 12 joules, but now I know that this is equal to the change in kinetic energy. Okay, now changing any quantity is final minus initial. So the final kinetic energy is going to be 1/2 times m, which is 2, times the final velocity squared, minus 1/2 times 2 times the initial velocity squared, which is 2 squared. So this is 4. So we have 12 equals v final squared minus 4. All right, add that over to the other side, and we get 16 equals v final squared. And then taking the square root is going to give us 4 meters per second is the final speed. Okay, so that's an example of an application of the work kinetic energy theorem. I'm going to give you another interpretation of work. So what you will learn in your calculus class is that the integral is actually code for the area under the curve. Okay, so if you have a graph of force versus position, it looks like this. The area under the curve is the work. Okay, so that area is the work. So there's kind of like, we can think about calculating the work analytically in terms of equations, like we did in this example, or we can think about it geometrically. If we're given a graph of force versus position, then we can use that to get the work. All right. So I'm going to put a box, or, well, I kind of already did put a box around that, but you need to know that fact. All right. So the previous examples are for one-dimensional situations. So we have a situation where the force points in one direction and the displacement is happening along that same direction. Okay, so force and displacement are happening along the same direction. Well, what if the force and the displacement are not in the same direction? Okay. All right. So in that case, what we're going to do is I'm going to give you a third formula for work, and it is F. So now the force is not necessarily in one direction, so I'm representing it as a vector. Dot product delta R, where delta R is the displacement vector. Okay? So this is one of the places where the dot product comes into play. All right, the dot product has come into play. So remember, there were two different ways of thinking about the work. Okay, or two different ways of thinking about the dot product. Sorry. One way we could think about it as the dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. All right. The second way we could think about the dot product is to do x component times x component plus y component times y component. So x component of the force times delta x plus y component of the force times delta y. And that is the, because the x component of displacement is delta x and the y component of the displacement is delta y. So these are two different ways to think about the dot product. Okay, so let's use this to do some examples. All right. Actually, we'll just do one example. So let's suppose you have an inclined plane of angle 30 degrees and length 11 meters. It has a, let's say, a 2 kilogram block at the top. Okay. The coefficient of kinetic friction is 0.1. Hang on, I gotta check something really fast. Okay. So that's the coefficient of kinetic friction. So the problem looks like this. We got a 30-degree angle. We've got a 2 kilogram block. The coefficient of kinetic friction is 0.1. And what I would like to know is, what was the work done by friction? Okay? What was the work done by friction? So, I'm not going to go through all the math, but it is possible to show that the force of friction is going to be equal to mu mg cosine of theta. So we already had our inclined planes lecture, so I'm not going to go through that again. But in this case, if you have a block on an incline that with no other forces acting, the kinetic friction force is mu mg cosine of theta. So that means that kinetic friction is going to be 0.1 times 2 times 10 times cosine of 30, which is 1.7 newtons. Okay? Now, if we think about this, this block, it's going down the incline in this direction. So that's the direction of our delta x, or our displacement. But the, so I should say delta r, shouldn't I? And then it is, the friction force is going in the opposite direction. Okay? So in that case, if I calculate my work done by friction, it is going to be equal to the magnitude of the friction force, which is, I'm going to use this version of the work equation. So 1.7 times the size of the displacement. It goes from this part of the incline to the bottom. So that's 11 meters times cosine of the angle between these two vectors. And we can see that that angle is actually 180 degrees. It's not 0 degrees because they're anti-parallel. Okay? Cosine of 180 degrees is -1. So we get 17 plus 1.7, 18.7. So our answer is negative 18.7 joules is the work done by friction. Okay? So that's an example of a problem of this nature. The other thing I wanted to talk about just really briefly is, I'll do one more example. What is the work done by the normal force in this same situation? Okay? Now, if we think about it, the normal force points perpendicular to the incline. So we have normal force goes this way. And the displacement is along the incline. Okay? So that's a right angle. So if we calculated our work done by the normal force, okay, it's going to be magnitude of the normal force, which it's not going to matter what it is, times the size of the displacement, times the cosine of the angle between them, which is 90 degrees, and the cosine of 90 degrees is 0. So the work done by the normal force is 0 joules. All right. Now, one thing that, so you might say, well, the normal force must always do 0 joules of work then. And that's not actually true. I can think of a couple of situations where the normal force does work. And one of those is if you're in an elevator, okay? So if you're in an elevator, here you are, the normal force points upward, and the displacement, because the elevator is lifting you up, is also upward. So they're actually parallel in that case. So situations where the normal force does work are situations where you have the floor itself is moving, okay? If the floor isn't moving, then the normal force isn't really going to do any work. Okay, so that's my lesson for today. So I will see you in the Zoom room.